You've probably heard of the giants of AI, right? GPT, Llama, they're everywhere. But what if I told you the future of AI might look nothing like them? Today, we're going to look past the headlines and explore the really exciting next-generation AI architectures that are quietly changing the game. Right, so we know the names. GPT, Llama, Gemini. They're the titans, for sure. But here's the thing. They all pretty much share the same DNA. So what happens when we start exploring the other branches of the AI family tree? What kind of crazy new things become possible when we challenge the very rules these models are built on? Okay, so before we can jump into the wild stuff, we've got to understand where we are right now. And today, one single architecture rules them all, the autoregressive transformer. It's the undisputed champ, the foundation that all of today's AI giants are built on. So this is basically the blueprint for modern AI. It all comes from that famous attention is all you need paper. It works by generating text one single word at a time, which makes it incredibly powerful and, really good at what it does. But, and this is a big but, there's a crack forming in this foundation. This architecture has a dirty little secret, a massive scaling problem that makes it unbelievably expensive to run. That scaling problem? That's what's kickstarting this huge quest for efficiency. Researchers are basically asking, hey, can we get all the power of these amazing transformers without the crippling cost? And the answer might just be in an old idea that's making a serious comeback: linear attention. So here's the core of the issue. It's called quadratic cost. And what that means is, in a normal transformer, if you double the amount of text you feed it, you don't just double the work. You quadruple it. It's because every single word has to look at every other single word, and it just creates this computational explosion. This is the bottleneck. This is what's holding AI back. Think of it this way. On the left, you've got the standard approach. It's like creating this giant spreadsheet where every single word is compared to every other word. Yeah, it's super precise, but it's a total computational nightmare. Now, on the right, you've got linear attention. This is way more like how you and I read a book. It processes one word at a time, just keeping a running summary in its memory. It's so much more efficient, but the trade-off is that some of those tiny details might get a little fuzzy in the summary. So if one is super precise but crazy expensive, and the other is really efficient but a little less precise, the solution people are coming up with is, well, why not just use both? This is the hybrid approach, and it's pretty brilliant. Models like QN3 Next are using this clever 3-to-1 ratio. They'll have 3 super efficient linear layers and then 1 really powerful full attention layer. It gives them this awesome balance of speed and raw analytical power. In this chart, this really shows you the payoff in the real world. As you feed more and more text into a standard transformer, its memory usage, what we call the KV cache, it just skyrockets. I mean, look at that bar. But then look at the hybrid model. Its memory usage barely even moves. This is the secret. This is what unlocks these incredibly long context windows, letting an AI process an entire book or a massive code base all in one shot. Okay, let's completely switch gears here. Forget about efficiency for a second, and let's talk about something radically different. If you've ever played with an AI image generator, you've seen diffusion in action. That's that magic where a blurry mess slowly turns into a sharp image. Well, what if we could do that, but with words? See, instead of generating text one word at a time, a text diffusion model starts with just a bunch of blank spaces, these mask tokens. Then, over a bunch of steps, it refines the entire sentence all at once, filling in the blanks bit by bit. It's kind of like a sculptor who starts with a block of marble and slowly chips away until the final statue emerges, instead of a writer typing one word after another. But of course, there's a catch. And it's a big one. Imagine you ask for a city, and the model tries to generate both words at the same time. It might see new and city as really common words and just stick them together, giving you New City, when what you really wanted was New York. The whole challenge is teaching the model how words relate to each other without giving it that one-by-one sequence to follow. So far, we've mostly talked about how an AI generates text. Now let's get a little deeper and talk about what it actually understands. What if an AI could not only predict the next word in a sentence, but could also predict what happens next in the real world? This is the wild idea behind something called world models. Just think about how your own brain works for a second. When you reach for a cup of coffee, you have this mental model that predicts its weight, its temperature, the mess you'll make if you knock it over. A world model tries to give an AI that exact same kind of predictive power, its own internal simulation of the world so it can reason about what would happen if. And this is where it starts to get really practical. Code world models are actually putting this theory to the test. Instead of just trying to predict the next line of code, they're learning to simulate the entire program's execution. They're actually tracing how data flows and predicting how variables will change step by step. It's a huge shift from just understanding text to truly understanding logic. All right, now for our final stop, and honestly, this one might be the most surprising of all. We've been told forever that in AI, bigger is always better. More data, more parameters, bigger models. But what if that's just not true? Let's check out how some tiny models are punching way above their weight class. This is the question that could flip the whole field on its head. We've been locked in this AI arms race, right? Just building bigger and bigger models, costing more and more money. But what if we've been looking in the completely wrong direction this whole time? What if the key to powerful AI reasoning isn't size, but something else entirely? What if I told you that a model achieved top-tier performance on a really complex reasoning test and it cost less than $500 to train? I'm not talking millions of dollars or even thousands, less than $500. And it gets even crazier. This model, it has just 7 million parameters. No, that is not a typo. 7 million. To put that into perspective, the big models have billions or even trillions. That's like comparing a bicycle to a rocket ship. So, how on earth is this even possible? The secret is recursion. These tiny models don't even try to solve a problem in one shot. Instead, they think about it over and over again, iteratively. A lot like how a person would solve a tough puzzle. They come up with a first draft of an answer, then they look at it, refine it, and then refine it again, getting closer and closer to the solution with each pass. They're achieving complexity through repetition, not just brute force size. Okay, so we've been on a whirlwind tour of some fascinating alternatives to the standard AI model. Every one of them has its own unique strengths and weaknesses. So now, let's bring it all together and try to map out what the future of AI architecture actually looks like. So here it is, your cheat sheet for the future of AI. Standard transformers, they're your powerful but super expensive workhorses. Linear attention hybrids, they're the marathon runners, built for that long-distance efficiency. Text diffusion is the sprinter, all about raw, parallel speed. World models, they're the deep thinkers, focused on understanding the why behind everything. And finally, those small recursive models are the specialists, the experts designed to solve very specific, very complex problems with incredible efficiency. So what does all this mean? It means the era of the one-size-fits-all AI model is probably coming to an end. The future is all about specialization. It's about having a whole toolbox full of different kinds of AI and knowing exactly which tool to pull out for the job at hand. So where do we go from here? Do we go down the path of pure efficiency, building AI that can process insane amounts of information? Or do we go down the path of deep understanding, building AI that can reason about the world more like we do? The future of AI isn't a single highway. It's a whole network of different roads. The only question is, which one is going to change our world the most?